So last maybe 2-3 classes or 4 classes before, we learned about machine learning techniques. Why? Because we saw how up-to-date regression can be connected to machine learning. So we saw, can anyone name a neural network which we used for regression? A neural network we used for regression. So it is known as MLP, multi-layer perceptron. Okay, so there we saw how there are Python, like one-liner Python codes, like functions, and if tools we studied, we saw there is an equivalent Python function for it. Just call that function, give the data, it will give you the like y cap equals to w0 plus w1x is the fit line. Then your job is in regression is to find the coefficients w0 and w1. So that's what we have been doing in regression using numerical methods. Okay, so we learned that in Python there are many functions which can be used just like that, like give your data and it will give you the coefficients as output. Okay, but then at last we saw multi-layer perceptron. That's a neural network for regression. Okay, right. So how artificial neural network is connected to numerical methods first of all. So whatever numerical methods you have learned, like root finding, bisection, computing derivatives, computing integration, solving ordinary differential equations, solving partial differential equations, solving regression problem, even solving optimization problems, all can be linked into artificial neural network. That is simple. The idea is you train your data. You need a huge amount of data to train. Once the machine learns from the training data set, you can do something on an unknown data set and predict what will be the case there. Okay, that's the machine learning concept. You train and then you test. Okay, training and testing. So similarly, we will learn into artificial neural network, and which is a specialized form of machine learning technique. So artificial neural network. So just by looking into these 3 words, these 3 words explain everything. First is artificial, it is artificial. Second is neural, that means neurons. Okay, neurons is in your brain, like millions of neurons. But in your brain, millions of neurons are connected in a very complex fashion, in a very complex network topology. There is till now no one has found what kind of network topology it is being connected. Okay, if it is connected in some of them, if it is connected in a specific way, class 7th or 6th, he will be solving ordinary differential equations. Okay, and so the brain cells are very high for them. So it depends how the neurons are connected to each other. So therefore, here also similar thing is applied. Like scientists thought that why we can't mimic the behavior of neurons. Okay, so then in order to create a machine version of ourselves, we have to the neuron concept, right? So it will be artificial neuron. It won't be biological neuron, rather it will be artificial neuron. So we will talk about one of the neuron today, that is perceptron. That's a very basic artificial neural network. Yes, artificial neuron, I should say. Perceptron is an artificial neuron. Okay, but you will see when we combine many neurons, when we combine many different neurons in a network topology, it will be artificial neural network. You will come to know that only neuron can't handle complex tasks. Suppose you want classification. I told you about classification. Banana, orange, apple. 3 things. How you can classify? How many? So you have a box full of trunk full of fruits. That is like apple, orange, and banana. Okay. So your job is you won't sit. Nowadays, people won't sit and count them 1, 2, 3. They want the machine to do it. So how you can apply machine learning technique to do that? So that's like classification problem. Okay. So what the machine will do? It will apply. It will just not work with a single neuron. Many different neurons are interconnected in a specific network and topology, and they will do this complex task of classification. So first we will learn about what is a single neuron. Then we will learn how neurons can be connected together in a network to make it call as an artificial neural network. It's a neural network. Okay, and they can do highly complex tasks. finally we will see a website known as TensorFlow Playground. I think already you saw it in your some other classes. So, but we'll see something. Okay, so sometimes like when you will need this artificial neural network and machine learning techniques, when? So if you have an equation, you don't need machine learning techniques. Usually, you can still use, but if you don't have an equation, that's where machine learning technique comes into existence. That means if you don't have an equation, that means you have data. Okay, if you have data with you, then machine learning techniques, artificial neural network techniques is beneficial to us. So therefore, what is usually the case? The case is like this. Okay, so usually scientists use model for predictions. Okay, they use different models for predictions. Like there is a weather model and they feed the weather data and they predict what is the case, like whether it will rain today, whether it is hot today or something like that. Okay, there is a model. So usually you have input data. Okay, usually you have an input data and you have a model here. Okay, you have a model and that model will output data. Okay, usually this is the till now. Okay, but what you will do if you don't have a model? Okay, so often we don't have a well accepted mechanistic model at hand. All right, so at that point, like we only have data, like experimental data. Maybe what time people come to class. If we do on a yearly, find an optimum time where students can come to class. But that's the data. You can't have a mathematical formula for it. Okay. So machine learning techniques could be useful in those cases. All right. So machine learning, what is machine learning? ML is the idea is like the prediction of any experimental data. It improves. Prediction improves with experience. All right, with experience. Prediction will involve like improve with experience. The more experience you will give to the machine, the more better it will predict. Okay, that's what is training and that's what is testing. It's another way to put it. All right. Okay. So this was said by a scientist. I don't know if you have heard of him, like T.M. Mitchell. Okay. So first part of like maybe 30-40 minutes will be a bit of theory behind it. Then we'll slowly move into a bit of math. So T.M. Mitchell wrote in his book in Machine Learning in 1997. Okay. So he found that a computer program like is said to learn from experience E. Okay, he gave it experience is a variable and he is saying experience is E. Okay, with respect to some class of task. Okay, that's the data set that is known as T. Okay, and in performance measure, like how good your machine learning algorithm is able to perform. So for that, he has denoted a like notation P. Okay, if its performance at task T as measured by P, it improves with experience E. Okay, so I will scan this note and send it to you, so I don't have to write it. Just the wording I wanted to tell is the start of ML. So the start of ML was like this. So machine learning may be useful to you when you don't have a model to describe a process. All right, I already told this. Only if you have data, you can use ML. Or maybe you have an incomplete model. The model is partial, like it's not yet constructed, but you know the model is giving you partial answers. Then you can use ML techniques to make it a complete model, like not a complete model, rather make the answer accurate. Okay, the predictions accurate. We have a model, but it's too complicated to solve. Okay, in those cases, so mostly like ML techniques is being used in partial differential equations, fluid dynamics. So usually nowadays, if you see, they use machine learning techniques in fluid dynamics, and their approach is to try to solve the Navier-Stokes, okay, which is one of the unsolved problem yet, millennium problem. But still, can ML be able to solve it? Okay. That's it. And when we have a ill-posed model, what do you mean by ill-posed model? Do you know? I the previous semester, ill-posed. Okay, I think when I was also doing my master's, I had this, I did not understand ill-post. It took a lot of years to understand what is ill-post for me. What I understood is this. Suppose you have a model. This is your model, mathematical model maybe. You have an input, and of course you have an output. Okay, but here comes the twist. You make a noise to the input, say some epsilon noise you are giving to the input, and of course there will be some change in the output. Yeah, because the input is changed to input plus epsilon, some change, perturbation to the input. Now the output won't be the same as output, right? It should also change. So maybe it changes by delta. Okay. Then if small epsilon, okay, if small perturbation to the input produces large delta, you can see now where am I going to. If a small change in your input is producing a huge change in the output, okay, that's like, then you can consider this problem as an ill-posed problem. This ill-posed problem is very different from the chaos concept which the previous group talked about. A small change in initial condition can result in huge outcome, huge difference in outcomes. But this is very different. Okay, ill-posed problem, like maybe your output changes in a very drastic way and it not converge. In chaotic systems, which they told, yeah, it gets converged to different orbits or different attractors. Okay, that's how chaotic systems and ill-posed systems are a bit different. They're not one and the same. So if you have an ill-posed problem, machine learning can come to your rescue. Okay. So yeah, this is what, and if some models are primarily data driven, if your model takes data as input, then for those data, machine learning technique is useful. So till now we are learning where machine learning algorithms can be useful to you. Okay. Right. Sometimes in machine learning perspective, the input is known as feature. We'll talk about this feature again and again. The word, I will not say input again and again, I will say feature. Okay, that's in machine learning jargon, they say input and feature are synonyms, like, okay, and output data you can say label. All right, so feature and label, this you will see most of the times in your neural network and deep learning machine learning courses. Mostly input and output words won't be used. All right, so in ML, machine learning computer program uses a training data. That means, what is training data? What is training data? Training data are those data sets which you have already questions, which you know the questions, but you also know the answers. That's a training set. Okay. Suppose you are classifying orange, apple, and banana, then you tell the machine, give the data that this orange looking thing is orange, this yellow looking thing is banana, and this red looking thing is apple. Okay, you give a lot of data set like that. That's a training data set. Then you predict. Then you ask, what is this? Then it will say, yeah, it's an apple. It's red. It's an apple. So therefore, training data set doesn't only include question, it will answer also. Then only the machine will learn. Okay. All right. So types of machine learning, we already learned about this, but through a different perspective. What are the types of machine learning we learned? Supervised and unsupervised machine learning. Okay. So regression comes under which category? Classification comes under which category? So good. So supervised learning, usually you find label of test data using feature. Okay. This is a bit different definition. I will just scan and give it to you. More about this, some more deep learning things I will not cover. That you will be covering, of course, in the next semester. So what is artificial neural network? We won't be covering ML, but what is artificial neural network? So artificial neural network is a technique in machine learning. All right, it's a technique in machine learning. Okay, so artificial neural network is what? Is how artificial neural network and machine learning are interconnected. Sometimes they are used interchangeably, and sometimes as a beginner you don't really know when to call it as artificial network and when to call this as machine learning. Okay, so artificial neural network is a technique in machine learning which is used for both supervised and unsupervised learning. Okay, so maybe I can write this. ANN is a technique in ML. All right, it's a technique in machine learning which is used in both both supervised and unsupervised techniques. Okay, both supervised and unsupervised problems. Clear? Okay, it's not like you will only apply to supervised and only apply to non-supervised. Okay. Good. So that's artificial neural network. Before learning artificial neural network, we should learn each individual neuron. Okay. So I think some of you already know in your brain. I should have drawn a better picture from biology. But anyway, think these are your neurons. Okay, these round are your neurons. Okay. Usually neurons are very they have a very nice structure. I like the structure. They have something like this, and then a tail. Yeah, yeah. So yes, and there is another neuron here which is very similar to this. Yeah, it's not a hen. Okay, not a hen. Looks like the hen, but so this neuron interacts. This neuron, suppose one is pinching you. Okay, so that's the neuron is getting transferred, but you should think how the neuron is getting transferred within 1 second or less than 1 second to a person, and he knows that you are pinching. Okay, within 1 second you know, right? But you have millions of neurons. How within 1 second or millisecond that information is transferred? And most important thing is neurons are not connected to each other. Okay, neurons, like this part is connected to this part, right? This is physically connected here. Okay, but neurons are not connected like this. Neurons are actually connected by chemicals. Here you will see chemicals here. Okay, so that's how, like, this will transfer electrical signal to this via this chemical, and these are known as like synapses. Okay, this is how they transfer information from one neuron to another neuron, so on till it reaches your central nervous system. Okay, so these are usually, I think, dendrites. Yeah, this is, I think, central one is soma, all these things. More of biological, bio AI. Anyway, so this is the sketch. This is the sketch. Okay, not sketch of neuron, biological neuron. Sorry, this is a sketch of biological neuron. Now, researchers thought, why can't we construct an artificial neuron? Why can't we construct an artificial neuron out of this, which won't involve biological chemicals and all those things, but will mimic in a similar way? So that is what is known as an artificial neuron, and we will learn about what is artificial neuron now. Okay. Anyway, so this was just a hint before we begin. We'll talk a bit about regression. I think we covered regression, how regression is a supervised learning. We covered it, right? Using the diagrams, we covered that class. So I don't need to cover that now. I think it's a repetition. Yes, maybe I'll draw the figure. So suppose these are your input, 1 and x. This is how regression I showed using an artificial neuron. So you can see how regression is actually an artificial neuron. Okay. W0 and W1 in regression. These are your regression coefficients. The fitting line, the coefficients. W0 plus W1x. Those are W0 and W. This is the summation. Okay. Then Z. Z is your activation function. You will apply Z to this output of this sigma. Okay. And you have phi here, phi of Z. Then this is your output Y prime, Y cap. Okay. Especially this node is for activation function. Activation function node. Okay. So what happens here? What happens? So this is a very important concept which I want you to know. Okay, which I want you to know. 1 and x, this is a constant input. This is a variable input. 1 is a constant input. X is a variable input. You are passing to W0, W1. They are multiplied. They have a dot product here. 1 times W0 plus W1 times x. That is fed here. They are summed up. That means W0 plus W1x. Okay. Then you are using an activation function Z. Okay. You apply phi of Z to this guy. Okay. Then your output is, depending on the activation function, your output is changed. What kind of activation function you will use? There are more, like many activation functions, but depending on your problem to solve, you will choose the activation. If you want to do classification, what kind of activation function you will choose? Okay. So maybe like you already know all these things. Tanith, ReLU, all this you know already. Oh. So usually few more terms like bias, okay, bias and weight. So which one you will call bias, which one will you call weight? Do you know? Bias is with bias is bias is something which is multiplied with a constant input. So bias is something which is multiplied with a constant input. So this is like bias, but this is a weight because it is multiplied with a variable input. Okay. So bias and weight, you know, this is like when you have constant input, and this one when you have variable input. Okay. So you can say which one now, which one is bias, which one is weight, isn't it? Fine. Okay. So which one W naught is? W naught is bias. W1 is most importantly, in regression concepts, your phi z, which is your activation function, is a linear function z. Phi z equals to z. Okay. You will see for other cases this won't be there, but in regression, note that it's a linear function. We are not doing anything. See, here itself we already have our answer W0 plus W1x, right? Now you don't need to change anywhere. So you take the linear function and it will just give you W0 plus W1x. So in regression, the activation function is linear. Okay, it's a linear. Phi of z equals to z. This is a very important concept. I will differentiate with another diagram soon. So this is a neuron. Okay, this is only a single neuron. Okay. So this structure, you can say it resembles an artificial neuron. Okay, it's an artificial neuron. Okay. Now slowly we will go to network where different neurons are interconnected to each other. Okay. So I already told about this concept. So a network of artificial neurons with properly selected activation function is known as artificial neural network. Okay. So a network of artificial neurons with a properly selected activation function is known as artificial neural network. That now you got another definition of artificial neural network, isn't it? So what is artificial neural network? We learned it's a technique in machine learning which can be used for both supervised and unsupervised learning. First definition. Second definition, what is artificial neural network? It's a network of artificial neuron with properly selected activation function. Isn't it? That's a artificial neural network. So I gave you two different definition of ANN, and which covers all the basic concepts of ANN. Okay. All right. So even you can do multiple linear regression. This is just a linear regression. You can similarly do this structure for multiple linear regression. What is multiple linear regression? So you have something like y cap equals to W0 plus W1x1 plus W2x2. Okay, so on till W1xm, isn't it? So now can you see how this diagram will change? Can you understand how this diagram will change? Now you have more weights. W0, W1, W2, similarly x1, x2. Now you can see how the diagram will change. So it will look something like this. All right. You can see now that the xi's have increased and the w have increased. Okay. You can see later. So in that way, I am trying to say how like there also activation function will be linear, phi z equals to z. For this one, I am trying to, can you draw for this one? This diagram, artificial neuron, can you draw from multiple linear regression? Can you draw now? Draw now. Okay, so suppose we have a training data set. Suppose you have a training data set tau or t, you can say, and xi and yi's, and you have n of them. This you already took in our regression class. This you already know about this notation, isn't it? So here label, suppose y is categorical. Suppose this is your classification, you of course will face categorical variables. Yes, happy with it. So y is like categorical, it won't be numerical. Okay, yes, no, pass, fail, like that. Good, bad, or something. Easier to represent. You can convert them also. In data analytics, we saw like maybe pass you can represent as 0, fail you can represent as -1 or 1. Okay, so it's converting, like transforming the type of data. Right. So if like classification, what does it do? Classification usually categorizes your data into different classes. That's another way to put it, isn't it? So you will have like a mango, orange, apple, then you have 3 different classes. But if you have 2 classes, if your number of classes, either it is pass, either it is fail, 2 classes, then it has a special name. Can you tell? The number of classification, number of classes equals to 2, number of classes equals to 2, then it is known as a specific classification. What is it? Yes, it's known as a binary classification. Okay, either 0. So binary classification. If your number of classes is greater than 2, if number of classes greater than 2, then it is known as multi-class classification. All right. These are a bit of theory first we have to see. Then I think I'll be covering what you already know. Anyway, I think you already know in your NLP class that all this. I think it's a repetition. Anyway, I'll try to cover it soon. So yeah. So again, for binary classification, you will have the same neural structure which you have drawn in your notebooks now. So, but the activation function phi z for classification will be, can you tell? One if, up to you. One if z is greater than 0. Z is a variable. One if z is greater than 0 and 0 otherwise. 0 otherwise. So you can see if this is your activation function, when you have that y data like W1, W0 plus W1 X1, all those data, the input, it will just apply this phi of z. Z is the input and it will just apply phi of z. If z is greater than 0, assign 1. If it is not, assign 0. So all the data points can now be transformed into zeros and 1. So it is classified, isn't it? So therefore, this activation function we were not using in regression. This is used in binary classification. In binary classification, but we were using phi z equals to z. That is the identity relation in regression, isn't it? So this is the only difference used. In regression, how depending on the task you want to perform, how the activation function changes. So therefore, it is said, if you want to do a particular task or achieve or predict a particular task, you have to change the activation according to your own use. Okay. So regression and classification problems lead to similar artificial neurons. Here also classification. Can you draw for classification is the same structure, but what is the difference in this? Can you tell? Activation. So identity activation function is used in regression, whereas you will use this step kind of regression function, step kind of activation function in classification. All right. Okay, cool. So here I think I will do an algorithm. I don't think you have seen this kind of notation previously. Here you have 1, so you will have W not here, then X1, right? You will have W1, so on, till XM maybe, and you have WM, okay? All this are coming together, okay, to sigma, all right? Then you have Z, applying the function phi, which is the activation function, and you're getting y cap, which is your output, okay? So I just want to mention this in form of an algorithm. It might be that you might be asked an algorithm for this. Okay. Maybe in your test or an exam, you might be asked an algorithm. Can you write an algorithm how a regression works from an artificial neural network perspective? Okay. So how? So first step one, what should you do? Step one, take vector input, isn't it? That is like a vector x of 1, x1, so on till xm. Maybe, yeah. Everyone happy with this, or there is an issue? Or more generally, you can write as this as x0 and say x0 equal to 1. Just to make the continuity. Second, what you will do, step 2, you use the vector of bias and weights. Okay, use vector of bias and weight. You know which one is bias. Which one is bias? W0 is bias. Why? It is being multiplied with a constant. Others are multiplied with variable, therefore they are known as weights. Okay. So use vector of bias and weights, that is a W vector comprising of W0 till Wm. Again, a column vector. Till now, okay. Then what you will do? Step 3, here many of them we just see they are multiplied, but there is a more stronger version of this. There is a more stronger version. You have actually vectors. Yes. So you actually not it's a dot product, it's like an inner product. Okay, it's just an inner product, and inner product the inner product of two vectors, if you are taking in R2 space, that's it's like a dot product. Okay. So generally it's an inner product. But for your dot product will satisfy. But if you're talking to a mathematician or talking to Andrew NG, like, then you have to mention inner product space. Inner product. Okay. So inner product, saying inner product is actually the more technically correct aspect. So it computes inner product, okay, of x and w. That is z equals to how? W transpose x. Okay. Go to Wikipedia and search about inner product space. And if you have a vector, how inner product looks like. You can see this notation there. So this is a vector, this is a vector. If you do W transpose x, it's just like turning W transpose. See, W is a column vector. W transpose, it turns to a row vector. X is a column vector. Now you can see a row vector multiplied by a column vector. You can easily multiply this times this. Okay. Then you will get a scalar, z. Yes. Fine. Then step 4 is after you get, now you have z, right? Now you have z, isn't it? What you will do now? You will apply the activation function to z. What is your activation function? Phi. Phi is the general activation function. So apply activation function. Apply activation function. Okay. Apply the activation function. That is, yes, you will get phi of z, and we are just assigning it to y hat for regression problem or classification problem. Now, okay. Good. So this W transpose X, I can write in a more simple way. How can I write in a more simple way? Wi summation of Wi, isn't it? Clear? Huh? Summation of Wi. So this is a structure of only a single artificial neuron. Okay. So despite their structural simplicity, single artificial neurons are very useful machine learning techniques. Okay. But many such neurons, when work together, they form an artificial neural network, and they can perform these complex tasks in machine learning. Okay. So therefore, there is why, if we can study this neuron at least, just that, and we are happy with it, then why the term is artificial neural network. Okay. Therefore, these single neurons, you will connect each other, many of them, and you form a network. That's what is known as artificial neural network. Okay. All right. So good so far. All right. We'll come to another one, the basic one. So which one is the basic artificial neuron to start with? already knew about, is it? No? NLP? It's taught already. Okay, we'll go soon through this. So you want me to cover this or? Seems like repetition. Anyway, so yeah. So a particular kind of artificial neuron is perceptron. Okay. So it's a particular kind of artificial neuron. Particular kind, artificial neuron. So what is the use of perceptron? Where you will use perceptron? Where you will use perceptron? Where you will use perceptron? You know, at perceptron is an artificial neuron, but where you should know where to use it. Else, yeah. So perceptron is used in classification, most importantly in binary classification, where you have like only two classes to classify. Okay. So perceptron, it uses the function which I already talked to you about is this one, binary classification, this activation function. Okay. Phi z equals to 1 if z greater than equal to 0, 0 otherwise. So this is the activation function perceptron uses. All right. All right, cool. So perceptron learning rule, this is where things will get interesting. Do you know how perceptron learns? Learning algorithm of perceptron? Yes. It's not that simple. Okay. Okay. So here everything will make sense now. Okay, here everything will make sense now. What I told 3-4 classes before, I told I showed you different graphs where you can find a decision boundary between the two classifications, isn't it? Now, how can you find the decision boundary? This is the perfect example where you can actually see the mathematical notation of decision boundary. Okay, so suppose you have two classes C1 and C2, and you want to classify your data into C1 and C2. Okay, that's the binary classification. So that means for a certain input xi, it will belong to either C1 or C2. That means C1 union C2. Isn't it C1 or C2? So if your W transpose xi, which is the case here, talked about W transpose X, isn't it? Oh. Okay. So W transpose Xi, if W transpose Xi is greater than equal to 0, what you will do? It means Xi belongs to C1. Okay. If W transpose Xi is less than 0, that means Xi is belonging to C2. Okay. So you can already see what is your decision boundary now, depending on these two quantities. You can see the decision boundary. The decision boundary will be a curve. It is not necessary that your decision boundary is always a straight line. It can be also a curve. Okay, that's given by W transpose X equals to 0. Isn't it? For less than 0, if something is happening, greater than 0, something is happening, then equal to 0 will be the boundary case. Okay. So this is how the decision boundary is found out. So now we will see learning of perceptron, and then we will see how in Python can we do this. So perceptron algorithm, shall I write here? So perceptron has a specific learning algorithm, which is not intuitive. The algorithm is there. It's just there. Maybe a specialized researcher or faculty in deep learning can say to you why the algorithm is like this. Okay. I will just write the algorithm here. So what is our job here? Why are we doing the things what we are doing? What is our job? What is our aim? Our aim is to find weight, isn't it? Our aim is to find the W not Ws, because then only you can do a regression, isn't it? So, but you know, in a single forward propagation, that weight is not that efficient. So therefore, Therefore, you do forward propagation, back propagation few times. That is known as epoch, isn't it? So therefore, this algorithm is to find the weight. This algorithm is to find the weights of a perceptron learning. All right. So suppose WK, what is WK? You know already that algorithm, it will iteratively perform the weight manipulation, right? Now it is W1, again it is W2, next iteration, W3, W4, till W100 it will be converging, isn't it? Yes. Yes. Hmm? So WK, what does it mean? WK means, what is WK? The weight after the kth iteration. Weight at the kth iteration, isn't it? That is the job. That is the job. Okay. Already learned about this perceptron algorithm rule. Maybe let me tell you, and maybe you can match up with that. Hmm? Okay, so you have an input. The algorithm goes like this. You have input, say xi bar. That's the input. Then what is the output? That is y cap. Can you tell me the output? So it should be phi of something, isn't it? Phi of z. Phi of z. Now what is z? Z is W transpose xi, isn't it? So yi had predicted you can get from this activation function applied to this input. Okay, so far good. Did you read through this notation? Did you read in this notation or a different notation? Different notation. Different. But actually this is like, if you want to be very precise, this is the algorithm. Because here you are using the inner product, dot product concepts. Okay. And is this enough? No. You have to scan through all the data points, I equal to 1 to n. Because you have suppose x1, x2, x3, y up to xn, y1 to yn. So this one is for particular ith state, and you are doing from 1 to n. Yes. Then you compute the loss function, isn't it? Loss function is given by, say I denoted by Li, that is yi minus yi hat. In regression also we are doing this too. Then so can you say me what will be the possible values of Li in binary classification? Okay. So after computing the loss function, which can take, that is 0, 1 and -1, our next step is to update the weights. So Wk you already know, so we need to find what is Wk plus 1. Okay. So we will update the weight, isn't it? So Wk plus 1 is equals to, obviously from numerical method, it will depend on Wk. Okay, that's fine. Then you are multiplying something R. I will tell you, R is your learning rate. Okay. And then with Li, which is your loss function, then with your input vector xi. Okay. So R is your learning rate. Okay, learning rate. And usually belongs to in between 0 and 1. It's up to you what rate you will fix. Okay, 0 and 1. But it should be a value between 0 and 1. Okay. It's user defined. R is user defined. So this method, you keep on doing it. Okay. The iteration, stop your iteration when you will stop. Think intuitively. Put your mind. When you will stop. When the algorithm should stop. When the algorithm should stop. When Li equal to 0. When your loss function is 0, your function is 0, loss is 0. So that's what you wanted, right? Basic thing. So when Li equal to 0, okay, when Li equal to 0, you have to stop your algorithm. Okay. So one most important thing I want to tell you, when this algorithm works, you tell me. You already know about perceptron. You already know about the algorithm behind perceptron learning rule. I want to ask you when this algorithm works and when it fails. it will fail. The algorithm will fail in some case, but what's that case? I want to know, and this is a very important point. That's the Newton method. There is some concept. Do you know about linearly separable data? Yes. Do you know? I told you, isn't it? I covered. Yes. So if your data is linearly separable, then your algorithm will work. If your data is not linearly separable, this algorithm will fail. Okay, till now. So this is one of the example for you. Yeah. This is the example for you question. I will show maybe in Python, like if you do it like, what is the thing here? It runs, isn't it? Every time in your house, like you turn on the motor to bring the water into your water tank, right? And then you use the water, isn't it? So this is the motor age. Maybe it has gone 15 months or 15 years. Okay, the unit I have not specified. Then after using for 15 years input, then we are doing a test whether the motor is good to use for future or not. If it is good for future use, it is passing the test. That is P. If it is F, then it is failing the test. That means you need to replace your old motor with a new motor. Is it? You got that idea? This is the data of that. Okay, from different households. So maybe one household 15 years fail. Need to bring a new one. 23 years need to bring a new one. 8 years pass. Okay, so you can see similarly. Now, if you plot this data set, that is y versus x. What is the y? Suppose here is the y. Maybe fail I will allow 1, and maybe pass I will allow 0. Okay. Then can you intuitively think that 0 is here, 1 is here, few values will lie here, and few values will lie here, isn't it? If it is clear, okay. Then can you tell me what's the decision boundary here? Decision boundary here will be a point, okay, because you only have one set of data, okay. So that point will be somewhere here. So this is like your decision point. Here, why first of all, can we apply the method we learned about perceptron here? Can we? Why? Yes, it's linearly separable. Therefore, you can apply. You can't apply because it's a classification problem. First of all, if it is linearly separable, yes, because by a single point you can separate. Maybe this is C1, this is C2. Those who are fail, maybe I allowed C1 category. Those who are pass, maybe I allowed C2 category. So these are all, oh no, this is C2, C1. Now it matches, right? C1 means 0, 0 means pass. Yes. So C1 category, C2 category. Then you can see this is a point which separates both of these data. So it's linearly separable. Hence, perceptron learning algorithm can be applied to find the proper weights. Okay, we will see this thing in Python. Okay. Okay, good. So sometimes when now you will ask, sir, like, why can't I see a line or a curve? Decision boundary is usually a curve like thing that you will see when you have two of x1, x2. X1, the two of the features, x1 and x2. Okay. So you will see here, maybe if I include temperature, x2, x1, x2. Temperature means after 15 years, the temperature is going to 40 degrees Celsius. Okay, which is very hot. That means after using your machine is getting very hot. Okay. So this is, you see, y is now depending on x1 and x2. In that case, if you do a separable thing, okay, if you do like plot between x1 and x2, there some of the data will lie in one region, some of the data will lie in another region. Okay, then say maybe this curve is your decision boundary. And decision boundary is not unique. You can have infinitely many decision boundaries. This can also be a decision boundary. Can also be, this can also be. The more closer you come, the more danger it gets. I told you about buffer in the class. Okay. So therefore, this is one of the limitations of perceptron, that in perceptron, it works for linearly separable data, but in linearly separable data, you don't have a unique decision boundaries. Isn't it? You don't have unique decision boundary. So that's like which decision boundary you will take. You have to find a lot of decision boundary and compare your efficiency. So in that way, perceptron learning rule is deficit in some case. That's a limitation. Okay. All right. So perceptron, this is the perceptron usually have infinitely many solutions. Therefore, perceptron usually has solution. If it is asked, say about draw a perceptron for classification problem, you will draw it. Then if it is asked, what are the limitation of perceptron? Then what you will say? Perceptron has infinitely many solutions, multiple solutions. So how you will know which one is correct? Perceptron is not reliable for test points near the group. This one. If your decision boundary is somewhere here, then it might hit to one of the points of the class. Isn't it? There it is your disadvantage. Okay. Perceptron works well with linearly separable data, and not all data are linearly separable. Yes, therefore this is one of your drawback. You can't apply to any data. You can't apply perceptron to any data. Okay. So what is the possible alternative? What is the possible alternative for this? Combine perceptrons. Combine different perceptrons. Okay. So combine an alternative is combine different perceptrons. Okay, combine different perceptrons to make it an artificial neural network. Okay. So yeah, so you already know about this, isn't it? Like I think you already know the difference between the regression and classification from the artificial neural sketch. Yes. How many have doubts in that? Everyone understood? In regression, what type of activation function we use? Yes. Linear identity. Huh? In classification, what kind of function you use? Sigmoid. Okay. Good. Fine. Another simplest neural network can you say? We covered perceptron. That's a single network, like single neuron. But another neural network which is very simple, can you say? FNN, feed forward neural network. Covered feed forward neural network. Yes. Good. So feed forward neural network. It's a unidirectional algorithm, unidirectional information flow from input to output, just one direction, no coming back. Okay. Once you have constructed a network of neurons, then apart from input layer and output layer, you will have something known as hidden layers. Okay. We did not talk about hidden layer when we are considering only a single neuron. When we consider of hidden layer comes, and we will see by playing on a website how hidden layer is effective in classifying. Why hidden layers are important. Okay, so hidden layer is a layer in between input and output nodes. Okay, yeah, and I think that is done initially. Yes, some activation function I want to talk to you about is some activation function. Okay, so first one we should look into is sigmoid. Is it sigmoid? So how sigmoid looks? So for sigmoid, what is the phi z function? You already now know that phi z, we are denoting it by the activation function. So phi of z, if it is equals to 1 by 1 plus e to the power minus z, it is like sigmoid function. You can use Desmos to quickly see how it looks. Okay. Similarly, you can use tan h function. tan h, isn't it? Tan h you can write as phi of z equals to tan h of z. That also depends on exponential functions. Can you write tan h in terms of exponential? Maybe in your class 12th, e to power z plus e to power minus z. If you see, I will try to plot it here, but it's already in your scan note. So hyperbolic tan will look like a s function. This is tan h. Okay. This is your hyperbolic tan h. Okay. Sigmoid will look like sigmoid. Careful. Fine. This is sigmoid. Okay. I should have used different color. Okay. So this is hyperbolic tan and sigmoid function activation functions. There is one more, two more actually. ReLU. Okay. ReLU. It's a good thing to call ReLU. So rectified linear unit. Okay. So rectified linear unit, also known as ReLU, activation function. How it is? That's what I told you. Like instead of a one, previously we were using one. If z is greater than equal to 0, it is like z variable. It's a linear unit. Linear unit. It is a identity unit if z is greater than equal to 0 and 0 otherwise. So it's very easy to plot the function for this, isn't it? Well, how? For z greater than 0. For z greater than 0, it is linear passing through origin. For z greater than 0, it is linear passing through origin and making a 4-degree line. Okay. For otherwise, if it is less than 0, it is 0. This is ReLU function, isn't it? One more is there, I think, if you have heard of it, soft plus activation function. Okay. In that, phi of z is log of this function. Okay. But why suddenly a very complicated function? The idea is ReLU function is not differentiable. ReLU function, is it differentiable? No, because it has a sharp edge here. So in order to approximate this non-differentiable function by a differentiable function, there comes another activation function known as soft plus. Okay, how it is? If I write here this ln 1 plus e to power z, if you draw, it will look like something like this. It is soft plus. Okay. So you can see soft plus is a continuous approximation of ReLU activation. You can appreciate it now. Soft plus function is a continuous and differentiable analog of non-differentiable ReLU function. ReLU function is not differentiable because of this sharp edge, but your soft plus is very smooth. Okay. Of course, you know about identity, where phi of z equals to z. Okay. Anyway, so there are many more activation function, and what we will do now is play around with TensorFlow. Okay. So with that, I think artificial neural network is okay each time. So this is the website here, like playground or TensorFlow. I think I heard from some already have seen this in your NLP. Anyway, we'll try to see again, but with some different flavor and taste. Okay. So we are doing a classification problem. Okay. There are 4 data sets here. Okay, so here you can see like we are doing a classification problem. Okay, I did not talk about regularization rate, so I am keeping it 0. Okay, but you will learn deep into in your further courses in deep learning and machine learning. Okay, so activation function, we have a lot of options here. We can use ReLU, tan, h, sigmoid, linear. We will take one by one and see which one is good. So learning rate I have fixed 0.03. You can vary 0 to 1. I don't know why it has more than 1 also. Usually it is 0 to 1. No? Anyway, so you have these two hidden layers. I will show to you that maybe like increasing the number of hidden layers can help you in classifying the data more efficiently. Suppose now we have two hidden layers. Okay, all good. Then suppose we are doing it. You can see test data and training loss. Okay, they are slowly converging. They are slowly converging, but they are parallel to each other. Okay, but the problem is it is not able to classify, isn't it? Is it able to classify? No, because this gradient thing you see, it should be around this only. Then you can say they have classified into. Okay, now it should look like a concentric ring or a circle, but now it is a different shape. Okay, so therefore we can see that this is not working. This is not that. He's trying hard, but he's trying hard, but it's not going. Okay. So you can see a lot of epoch has been done. And however you wait, it might not be able to reach or might take a lot of time. Hmm? Okay. So now what I will do is increase the number of hidden layers. Now there are two hidden layers. I will increase the number of hidden layers. Okay. Okay. Mm. Okay, let us see now. Okay, wait. I think we don't need to increase the number of hidden layers. Maybe this one, will also work for you. But here, the number of neurons. Okay, we should increase the number of neurons in the hidden layer. Okay, maybe I'll increase the number of neurons in this hidden layer. Okay, I have done 3, 4, 5 now. Maybe let us see now. Okay, now you can see better, right? Now it is able to classify. It is able to classify the two groups. You can see this is your decision boundary here. Okay, it was like orange one and blue one. You can now see orange one is in the, so the space or region that is colored orange, at those regions orange points will lie, and the region which is colored blue, blue points will lie. Okay, that's how it is able to separate the orange and the blue points. Okay, that's how classification is done. All right. So you see how increasing the number of neurons in the hidden layer can help you solve the classification problem more efficiently. This is tan H. Okay. Wait. Maybe can we try with ReLU? Let's see if it is able to. Yes. But you see one observation here. In ReLU, the outer boundary, the boundary which you saw previously, is not the same as this one, isn't it? Why? Hmm? Why? Yes, because ReLU function, we already know how it looks. ReLU function is made up of straight lines. Yes. So therefore, you will see that the decision boundary also involves straight lines, made up of straight lines. But not in other cases where the activation function is actually continuous and differentiable. There you will see a very nice circle, isn't it? Okay. So now ReLU also did this job. Let us see. Do you think sigmoid will do the job? What do you think? Sigmoid is taking a lot of time. But will it be? Because I have supplied a lot of neuron in the hidden layer, but still it is facing a bit of difficulty. It is trying to, but we know this is not the decision boundary, of course. Yes. So anyway, it stopped there. Okay, because you can see the convergence here. We will see this structure again till how many iteration we go. We almost likely to see same structure. Okay. So sigmoid is not working. Do you think linear will work? No, because obviously because the data set is like that, it is not linearly distributed. Linear, you can see how the gradients like lines are there. Hmm? Okay. it's already converging and it's not able to classify our data. Fine. Okay. Now, so which one wins? Which activation function wins this data set? Tan and ReLU. Okay, Tan and ReLU were able to classify. And in both of the cases, we saw the decision boundary were different. In tan H function, we saw it was a regular circle kind of curve, decision boundary, but in ReLU, we saw it was made up of straight lines, okay, like a hexagon or a heptagon. Okay, so now let us move to the next data set. This is your data set, which is more even complex. You see how the data set is being distributed. Two blues are here, two oranges are here. Now, how decision boundary can be formed in this? Okay. So intuitively, you can picture out how it will be formed. Okay. Okay, let us take tan H. Let us see. Very nice. So you can see how nicely it is able to classify. Okay, orange dots are in orange region, blue dots are in blue region. Yes, good. Is a ReLU able to do? Yes, almost yes. Okay, because again, straight lines are involved. Again, you can see the boundaries are like straight lines. Linear won't be able to do it. We already know. Sigmoid. Think so. Okay. So even in classification problems, you can see depending on the data set, tan H and ReLU are your most preferable choice if your data is very complexly distributed. Okay. Oh, it did, I think. It did. That is good. It did. So, yeah, it classified, isn't it? So, sigmoid is also helpful. Good. So, all right. Now, about this. So, which one you think will linear work here? You can just put a line over here. You can just put a line and I think it is linearly separable. So, it is already being done, isn't it? So, tan H and all, it is very easy for them. So, we will just look into linear, whether linear is being done. You can see yes. Yeah. So in linear activation function, you can see that orange are still lying in orange region, blue are still lying in the blue region. Okay, fine. Fine. Now this is the toughest data set. Okay, this is the toughest data set to classify, which looks like this. Now, how you will classify this? Okay, how you will find a decision boundary to this? That's the question. Okay, so let us use tan H and see. It is actually trying to, but the decision boundary it found out is also not that trivial. I don't think it is that trivial. Okay, but let's see. See, this one, it is trying to go into that spiral motion, isn't it? It is trying to align into that spiral motion. But no, I don't think so. But it's very slow, I think. Okay. But yeah, anyway, we got a concentric circle over here. So it is trying to do it. Okay, trying to learn and do it. Okay. So if I am not able to do in this class, your job next class is to show how to classify this. Okay, using this tensor. Okay. Tan H, so what should you take ReLU? ReLU. ReLU just made of straight lines. So we can't think how straight lines can be made into fit into this thing. Okay. So how to do this classification? I want to know from you in the next class. We'll increase the neurons. This one or this one? This one. Yes, this one. Fine. Shall we? Tan H. So we increase the number of neurons in the second layer and we are applying tan H activation function. Let us see. This did not work. Assignment. Okay. Your assignment for next class, apart from this theory, computational assignment, that one is theoretical assignment. The computational assignment is to show that it is able to classify this data. What kind of parameter you will fix so that this data is being classified. Yeah, it's not that easy to. So it is very simple data, isn't it? Like it's just arranged in a spiral way. But how this complicated, even high neural network, artificial neural is not able to do. So you have to find which kind of configuration, how many layers, hidden layers. Maybe you have to increase the number of hidden layers. See, this is a very nice approximation. It's a very nice approximation. You can see this one, the part of the blue is already being aligned to this. You can see this one, isn't it? Did not cover all the things, but most of the blue part, and I think it's a good classification till now. Whatever we learned till now, it's a good classification. You can see most of the orange region are in orange dots. Most of the blue dots are in the blue region. Most, not all. Like this part, you can see it is incorrectly classified because blue dots are lying in the orange region, isn't it? So can we reduce it? That will be your assignment next class. In computers, you show me the output. Like I should see how it is classified for in different systems. Okay. So this is fine. Yes, and one more thing I want to show you is the perceptron learning algorithm. So just see in your note, like where you have written that perceptron algorithm, where we were updating the weights, isn't it? We were updating the weights, right? So how WK plus 1 equals to WK plus learning rate times the loss function times the input, Excel. Yes. So yeah, so same thing for the same data, like the motor data. We are taking the motor data, okay? We'll solve for both. That is only one X variable, the age of the motor and age and temperature of the motor. So we can see the point. We'll see a point and also a line decision boundary. So you can see here, like this is the algorithm for it. The maximum number of iteration is lot here. And this is I have X and Y I have taken here. Fail is 1, pass is 0. Okay, you see how X is the number of years I have stored and Y is the pass or fail. And here just the D type, like how many bits it will store. Okay, I'm just assigning. Maybe it will just store integers from -127 to 127. Okay, in that way. Learning rate I have kept 0.01, fine. Loss function I have defined as the same size as of X and Y. N, okay, N. N is the size of X. Okay, N is the size of X, fine. Till now it is fine. So same size we have to do for the loss function, isn't it? Same data set as X and Y, length. So you have to take the loss function as the same length as the X and Y. So here I have calculated the W, I have initialized all to 0. There are two weights, I have initialized all to 0. Okay. Then from 0, they will keep on updating as the number of iterations pass. Okay, that's the learning algorithm. So see exactly notebook, what I have written is exactly the same or not. So Z is the function here, W0 plus W1 xj, fine. Then passing this activation function Z. What is this function activation? Return 1 if Z is greater than 0, 0 otherwise. You see this line. All right with you? Classification, two classes. Okay. Fine. Loss function is yj minus y hat. So it can take either 0, 1 or -1. So then I'm just doing W equals to W plus learning rate R into loss function Li into the input X. Isn't it? And when I'm breaking it, if loss function is 0, you break. Isn't that logical? That's the stop criteria of your algorithm. If your loss function is 0, you break, right? So what is your loss function? Loss function is B equal to 0. B equals to the norm of the loss function. You can see here, B is equals to the norm of the loss function. Okay. So if B equals to 0, you break. And what is it printing? It is printing I and W. I and W. What is I and W? I is the iteration and W is the weight. Okay. Fine. So we will see, and this is the separation line minus W0 by W1. Fine. So you can see from here when your data, I will share this code with you. You tell me what is the point of separation in the next class. Okay. What is the point of separation here? Fine. This is just a simple model, isn't it? Now I will try to show you the next model where exactly the same, but instead of just motor age, we will have motor's age and also the temperature of the motor. Okay. So then we will see, like if you plot, then we will have two features, isn't it? Two features, x1 and x2. One is the motor age and another is the temperature. So now if you plot x1 versus x2, if you plot x1 versus x2, some of your data will be in one cluster, some of the data will be in another cluster, and you can find the decision boundary by computing W transpose X equals to 0. Because if W transpose X is less than 0, maybe it lies in this category. W transpose X greater than 0, it lies in this category. So this is the decision boundary. So we'll plot exactly like this in this case for the data I showed you. Okay. So this is the data already defined for you, x1, x2 and y. Learning rate is 0.01, fine. So everything is same. But here the z is different. Instead of w0 plus w1x, one more term we have w2 plus x2. Fine with you? Okay. So it is scattering over here, like fine. Then loss function is determined. Okay. And then this is our algorithm here. Same algorithm. Same algorithm, isn't it? Then again, I and W, then you plot the decision boundary, which is this one. Okay. This is the equation of the straight line. You think why is the case? W transpose X equals to 0 in this data set will turn out to be an equation of a straight line. Okay. Fine. If you run it, okay, if you run it, you are displaying a lot of data sets, fine. But where is my figure? Okay. Yeah. So you can see the green is one category, red is one category, and this is one of the decision boundary lines. And I feel it is not a good decision boundary because it crosses red. Okay. Another decision line could have been drawn like this. So you can improve this algorithm according to your choice. Maybe learning rate you improve it 0.01, maybe 0.2 or 3 you can make so that it can estimate a proper decision boundary. As you already know, decision boundary is not unique. You can have infinitely many decision lines. Okay. And therefore perceptron has infinitely many solutions. Good. So this is what I wanted to cover. And yeah.